Welcome to Unite Now, where we bring unity to you, wherever you are.
Hello everyone. Today I will present you a set of visual effects from the Spaceship demo and how they were made and integrated into gameplay. My name is Iche. I'm a visual effects artist at Unity Technologies in Paris, working on visual effects graph and making effects for the Spaceship demo. Just as a reminder, Spaceship Demo is a high-end graphics demo focusing on visual effects. It is rendered using our HD render pipeline, and it relies on VFX Graph for all the visual effects. This project featured AAA production cases, from simple, realistic, and dramatic environment VFX to more elaborate, interactive, augmented reality UI. So feel free and take a look at the project as it's available at GitHub at the following address. And without further ado, let's take a look at the demo.
Hello, Baker. Can you hear me? I hope you made it safely down there, and I hope you can hear me. I can't hear anything. The whole system's busted. There you are. I see you in the monitor now.
Security check in progress. Access granted.
There's a secure shell terminal there, just where you are. Put in the coordinates and get us to the landing site. You have to get us out of here now. Hurry up and get us to the landing site.
Select landing target.
There it is. Hurry up, we don't have much time. Hurry up. You have to get us out of here now.
Landing target located. Attention. Multiple weapon signatures detected.
Son Baker.
Shield taking damage. Power down to 32%. Substantial damage to shield. Power down to 17%. Shield power down to 9%. Core energy depleted.
Sorry.
Shield has been deactivated. Immediate evacuation. Proceed to the tenders.
Pretty cool, right? Today we will focus on different production cases and the benefits of using VFX Graph both for workflow efficiency, creativity, and optimization. Sequencing effects into complex timelines of events, making visual effects react to the gameplay by integrating them into scripts, creating bounds between the environment element and the visual effects, using shader graph in order to enhance the visuals, and finally, an optimization case we implemented to reduce the number of instances in the scene. Let's start with our first example, how to orchestrate visual effects during the attack sequence. The attack sequence follows a precise timing and scripted scenario, and in order to achieve that, everything is driven by timeline. All the action takes place both in the bridge room with its holographic table and in the core room. During this sequence, the player is free to walk around and look at different elements as all the environment destroys gradually. During the attack sequence, enemies have located your ship and launch a deadly and devastating attack.
Attention.
The main screen changes to an overview of the battle and you see a rain of missiles crashing onto you, shaking the camera on every hit and destroying all the environment around you.
Power down to 32%. Power down to 17%.
From the lookout of the core room, you can see the ship's energy source getting depleted as every hit drains its resources until it collapses.
Shield has been deactivated.
Finally,
Immediate
you
evacuation.
take a lethal blow before blackout. Right now, let's get an overview of how this sequence is set up. The whole sequence is orchestrated using 3 different timelines. Every of them is in charge of a precise task. First, the main timeline. This is the master orchestrator of the whole sequence of events.
Power down to 30%.
It's driving other timelines and assumes voiceover, audio, and scripting sequencing.
Substantial damage to shield.
Next,
Power
the
down
core
to
depletion timeline.
70%.
It handles the control of the core depletion animation
Shield power
and
down
its
to
collapse
50%.
at the end. Finally, the core hit timeline handles the repeating animation of the core every time a missile
Immediate
hits the
evacuation.
spaceship.
Proceed to the tenders.
Now that we have an overview, let's focus on how the core reacts to the missile hits. The main timeline is periodically broadcasting hit messages to the world,
Multiple
and these
signals.
messages can be intercepted by the scene elements in order to perform different scripts. Among these, one is in charge of playing the core hit timeline that spawns electric arcs, shake the core, and distort the rings. In parallel to the reaction of the hits, the core is depleting and ultimately collapses. The core depletion timeline is started in a pause state and wait for messages from the main timeline to play. So every time a core depletion message is received, the timeline resumes its play and will stop at precise time, waiting for another message. This timeline controls the power exposed property of the core VFX. And power is just an artist-defined property that drives the visual of the effects using a single slider.
Shield power down to 9%.
Finally, a collapse event is set to spawn additional particles for the core collapse and shut down other particle systems. Finally, let's focus on animated destructibles and how we trigger them. During the final attack, there are 2 kinds of messages we use for missiles: hit and hit strong. And every hit strong message, a main state machine changes its state to the next one. The main state machine represents the degree of destruction of the scene, and changing to a newer state releases new destructible animations. Every destructible prefab is controlled by its own state machine and changes from idle to playing state whenever the main timeline tells it so, thus releasing the rigid body animation, VFX, and sound effects.
Shield has been deactivated.
Impressive, right? While this was a pretty straightforward sequence of events, the demo also features interactive elements that can be hovered and used by the first-person controller at any time. For example, the first interactive we encounter is the login button in the security room. It can be hovered in, out, and can be interacted using the mouse click or a button press. When interacted, it disappears and triggers another script, in our case the login sequence timeline. Let's take a look at a very simple example. This interactive item blends between a square shape and a circle when hovering. And if the player activates the interactive item, a bright circle outline appears. The visual effects expose a Boolean property named enabled that defines the visual of the interactive element. And in order to display the activation circle, a validate event is sent to spawn an additional background circle. Every interactive element uses the same script, AR/UI interactive. These scripts rely on the collider component to perform distance check and raycast from the camera. Upon validating, a script action is triggered to send the validate event. Upon hovering in and out, 2 other scripts control the state of the Boolean property. Let's see now how it's used in the graph. There are two distinct systems used in this effect. The system on the left spawns an everlasting particle. Its start spawn input is connected to the validate custom event, so it's only started when the script sends the event. The system on the right has spawned an everlasting particle, and the Boolean property is processed by the graph to animate the alpha attribute value that we use for a different purpose here, control other attributes and property. This will change the shape and the size of the particle from a small red square to a big blue disk. There are many more use cases in the demo of the AR UI Interactive, but all of them use the same scripting and authoring base. Another benefit of using VFX Graph is you can easily create bindings between your scene elements and your visual effects. During the attack sequence, there are many electric cables being torn, swinging around, and releasing bursts of sparkles. These cables are made 100% using VFX Graph and benefits of the rigid body physics to animate. The setup in the scene is comprised of a cable VFX rig composed of all the cables and the sparkles effect. This effect is integrated into the scene by attaching a rigid body setup and a script that triggers both the animation and the sparkles. Here's a simplified scene with the cables prefab. Let's take a closer look at one set of cables. In order to simulate the rope, we use a chain of capsules rigid bodies constrained by hinge joints components. And as we are dealing with electric cables, we need them to be a bit stiff, so only 3 elements with high damper coefficient will do the trick. When pressing play, the cables are simulated as rigid body and impulse periodically, releasing some sparkles. Now let's take a look at the VFX. It's an all-in-one configurable set of cables that is configured with the VFX property binder. This property binder using a multiple position binding that bakes the 4 point of the rigid body chain in real time into a texture and sends it to the visual effects. This texture is used in the graph as a property of the sample multiple position map operator that computes position of a Bézier chain with automatic tangents from a multiple position map. This drives the cable's curvature along the chain of rigid bodies. In order to spawn the sparkles, an additional system is used to spawn particles at each cable's end. There are 2 kinds of sparkle bursts that can be spawned. A small burst when the cable will get a shaking impulse, and a big burst of sparkles happening once when the cables are torn. These 2 events are handled by the onShake event script to spawn a burst of sparkles when a camera shake happens, and another script will toggle a burst of sparkles and an impulse to the cable within a delay between 1 and 2 seconds to simulate a surge of the cable. Here's the result in action. The cables break and start their power surge loop, but they can also react to the camera shakes as well. Another benefit of using a VFX graph in Spaceship Demo is to benefit the bonds it created with shader graph. In this part of the presentation, we will showcase 2 distinct cases where shader graph was used in order to perform custom rendering and improve quality of effects. First, using shader graph on simple mesh in order to create augmented reality HUD elements and use the VFX graph operators to perform property control on these shaders. Then we will showcase a new feature of Unity 2019.3 that lets you use shader graph for particles. And in this example, we will use shader graph in order to create simple anti-alias trails. Let's focus on the first shader graph example, controlling shader properties of simple meshes from VFX Graph. At the beginning of the demo, the player HUD performs a startup sequence and displays some computer log information. During this sequence, the environment is highlighted by an overlay effect that reveals the shapes of the surroundings in the corridor. This effect is called an outliner, and while it's subtle, it's adding to the cosmetic sci-fi value of the HUD startup. We recreated a simplified scene with only the outliner in order to showcase things. In this scene, 2 versions of the outliner are present, a simple and the final version with randomized animation. When looking sideways, we can see the progression is quite straightforward. And when adding some randomness, it's still a progression, but it feels more glitchy and erratic. The graph in itself is quite simple. It doesn't contain any particle system, but instead two output mesh contexts. This context only display a mesh rendered with a standard shader or a regular shader graph at a given transform. And all the properties of the shaders are exposed as slots in the graph. These contexts are controlled by a set of operators that perform the animation of the elements from close to far. The first set of operators compute the distance between the element and the player's camera and computes a startup delay based on this distance. The delay is then applied to an animation curve for the blinking effect. So all the elements are enabled at once, but they will animate accordingly to the distance of the camera. The result of the blinking curve animation is then used to control the display of every element, basically its scale and opacity. Now, let's focus on the shader used for this effect. First, the outliner displays a fill effect. This effect covers the whole surface of the object, but also on non-visible geometry rendered behind opaque object, slightly less visible. This fill is achieved in the shader using non-Z-clipped alpha blending. So the pixel will render regardless if they are occluded by opaque geometry. Using a bias screen space dithering pattern and blending between two different opacities, behind the object or the object itself. An inverse Fresnel is also applied to the opacity in order to make the effect appear less flat. Now let's focus on the outline effect. This effect renders a flat color outline around the object edges to highlight its shape. This effect is also using an output mesh context with the same mesh, but this time it renders a flat outline using a vertex push method. Basically, the shader only renders the back faces and will push the vertices a bit along the normal so the mesh expands. When clipped with the regular object, only the outline appears. In order to control the width of an outline, a distance test is made, so the further the object is from the camera, the more push it will require in order to keep a rather constant pixel size on screen. We just saw that shader graph can animate shader properties on simple meshes in VFX Graph, but it can also be used in a quite similar way on particles. During the attack sequence, the holographic screen displays an overview of the battle and all the missile trajectory information. These trajectories are rendered using VFX Graph as particle strip trails. These trails can be rendered using different kind of outputs. First, you can use an output particle strip line, so it will render the trail as a 1 pixel wireframe line without any kind of anti-aliasing or chance to make it thicker. Alternatively, you can use an output particle strip quad to render the trail. So it will enable a defined width, but still won't do any anti-aliasing. So in order to add anti-aliasing, we will be using a VFX shader graph. And this special kind of shader graph will change the context input so we can pass the particle color and alpha to the shader. The shader graph in itself is quite simple. It performs remapping of the U-axis, so the UVs goes from 0 to 2 in one case and from 2 to 0 in another case. These two gradients are clumped into the 0 to 1 range using saturate, and then we multiply the one by the other. So the result is a reflected gradient that we multiply with the particle alpha. This gradient is then used as a lateral alpha mask for the trail so that all the edges can fade instead of clip harshly. This results in a smoother rendering that acts as anti-aliasing when used on thin trails. The final example we wanted to showcase today is highlighting visual effect optimizations. During the production of the demo, we added a camera shake system to simulate the spaceship poor condition and the missile impacts during the attack. In addition to the camera shakes, we wanted sparkles to be spawned from multiple sources around the player. The first design was using one visual effects per source, and a script did attach to the shake and its message from the gameplay to start these effects. Also, the script did set an intensity property of the visual effect to scale the probability and the amount of particles of each source, depending on the desired shake intensity. Inside the graph, the spawn contexts were using probability sampling to determine whether the source should start or not, and if it was started, how many particles to spawn. The system was pretty straightforward, but it had a drawback. It involved many sources with only few particles. In our example, we have 18 sources in the first corridor, and every source is performing 4 draw calls for 3 systems, which is totaling into 72 draw calls and 54 update calls at peak. When added to other sectors' instances, it could grow up to several hundreds of unnecessary update and draw calls. While it's convenient to prototype this effect using a naive method, it is good to optimize this later when you are close to ship your game. This benefits by reducing draw calls, maximizing the efficiency of the simulation by merging instances per sector into master simulations. In order to factorize sources, we implemented a single effect per sector that was configured with a list of sources baked into a point cache. Using a VFX property binder, we wrote specifically for that purpose. This property binder is baking all position into one 2D texture and all forward vector for each source into another 2D texture, then set this texture as properties to the visual effects. In the graph, the spawn logic was modified in order to perform the probability sampling not in the spawn context anymore, but in the initialize, by performing early kills and iterating on all the source pixels in order to determine which source was supposed to spawn at which intensity. Finally, instead of using a property for the intensity, it was transferred to the graph in the event attribute payload, stored into the size attribute. Using this slightly more complex method, we were able to decrease the instance count for this effect to only 5 instances, 20 draw calls and 15 update calls. And we are done for all these practical cases. So, what did we learn from this? First, we can say that VFX Graph is really efficient at integrating into systems, such as timeline and C# scripting, and even those it's not most compatible with, such as CPU physics. The simple interface to control properties and events and its bonds with shader graph makes it a choice for technical artists. And the property binders are a huge help, as they save you the time from writing over and over C# code to perform bindings between effects and the scene. And they can even help you bake multiple effect sources into cache textures in order to optimize the number of instances in your scene. There are many more cases that are showcased in the demo, so I invite you to download the project, open it, and follow the discovery guide we provided.